Excellent. Okay. So as I said on Monday, we're kind of starting a whole new kind of section today, this week, when we start talking about integration. And so how we started was we started looking at functions, right? So we had functions, so let's call it f of x, measures something, and we do this thing called differentiation. And f of x became f prime of x, or dy dx is another way to do it. So y equals f of x. We had this, and we went from a function to a rate of change. Right, so if our function was something like distance, and we've got a function as a rate of a function as a function of time, then the rate of change with respect to time would be velocity. Okay. So let's sort of go the other way now. This time we're going to start off with a function which is going to be a rate of change. And then we're going to do something called integration. And we're going to get a new function here. So let's think for a second what kind of function that would be. So if we have a function and we're looking at its rate of change, what is the relationship then of the initial function to the rate of change? So for example, we go things like distance traveled to velocity, some measuring something, and then we get a rate of change, so it's something per whatever the input is, per time or per distance or whatever. So what we get here, we could call an accumulation function. Just to call it something to describe what it is. So if we are getting something, if we are getting, $10 per day, then we're accumulating money, right? If we are traveling 10 feet per second, then we're accumulating distance. Whatever it is that's being differentiated, if we go backwards, we're just like accumulating that thing. So accumulation function is a good way to describe it. And so later on, we're going to see that we're going to have a notation for it. We're going to call it like this. So this is kind of like a really elongated S. And here we've got the dx, the same dx that we get here. Right, so let's think in terms then of distance and velocity. Okay, so if we have a function that gives us a distance traveled, then we've already seen that when we take the derivative, when we do like delta y over delta x, like a little bit of distance traveled and a little bit of time, we look at that ratio, that gives us, that approximates the velocity we're going. It's actually equal to the average velocity over that delta x. And as we make that delta x smaller and smaller and smaller, we've seen how that goes to a limit, and that we can say, well, that is the actual velocity that we're going at that point, that instantaneous velocity. And so to go the other way, we've already done things like, well, if f prime of x equals delta is approximately delta y over delta x, then delta y is approximately f prime of x times delta x. Okay, so we can actually figure out how much we've accumulated over that little time period by multiplying it by the derivative. Okay, this is this process of integration. Okay, so if we talk about just in terms of velocity, right? Velocity equals distance divided by time. Well, we know that distance then is velocity times time. Okay, so if we go 30 miles per hour for an hour, then we travel 30 miles. Okay, just like if we travel 30 miles in an hour, we're going 30 miles per hour. It's just like the same thing going sort of back and forth. Okay, now, so that's not, I'm not saying anything really difficult there, right? What is hard? Well, what is hard, what we saw is we looked at situation where the distance that you're traveling sort of goes at different rates at different times, right? So that's why we had to talk about a derivative to make sense of what happens when distance it varies over time. The same thing here happens here. What happens if velocity varies over time? Okay, we can't just do one big velocity times time calculation. What we've got to do is we've got to break it up into little things and figure out how much velocity, how much distance we've traveled over every little time interval. And then if we added all that up, we get the total accumulation of distance, and that's integration. That's basically what we're going to be doing for the next 6 weeks or so. Okay, we're going to, and just like we did this with differentiation, remember how we went through a whole kind of process and eventually we came up with formulas? We're going to do the same thing with integration. We're going to go through it carefully, define it properly, get a good feel for it. And we're going to see that it's both a geometric and an algebraic thing. And then eventually we're going to end up with formulas. So it's going to be a kind of like a similar kind of process. And along the way, we're going to see various applications that you use for it. So for example, accumulation function. You can already think about things you can accumulate. We've already talked about accumulating distance. You can talk about accumulating money. Okay, so if you've got some investment over time, if things change, you're going to be interested in how much money you have at the end, how much wealth you accumulate at the end. These are the kind of problems that we're going to be dealing with. Okay, so, and as per usual, we're going to do things 3 different ways. We're going to have a look at things numerically, we're going to have a look at things graphically, and we're going to look at things with formulas. And we're going to go back and forth between all 3. So let's start off with something numerical, because that's, I always feel that that's something that's kind of more tangible and you can get a good idea of what's happening from that. So let's have a look at a distance problem, except we're given velocity. So let's say this is, so we've got something and we're measuring the velocity over a 10-second period. So this is going to be feet per second. Okay, so we've got an object and we know how fast it's going. What kind of question can we answer? Now, we can't answer the question, where is it? Because we don't know where it started from. right? Because, you know, like if you're in Colombia and you do a certain set of speeds, and you're in St. Louis and you do the same set of speeds, you travel the same distance, right? But you're in two different places. Okay. All we can measure is the accumulation, right? How much is the total distance that we've traveled? So we want to estimate distance traveled. Okay, and so we can go about this in various different ways. We can say, okay, for the first 2 seconds, maybe we went 20 feet per second. And so I'll measure times that by 2. And then I've got 2 times 30. Estimate what happened between 2 and 4. Between 4 and 6, I'll say we did 38. Between 6 and 8, 44. And between 8 and 10. Okay, this is a legitimate way of estimating. What I did was in each interval, I picked a velocity I was going, and then I just multiplied it by the time. And that will give us 40 plus 60, that's 76, that's 88, 96, equals what's that? That's 100, 64 plus 96. Add that together, 260, 360. Okay, so I came up with an estimate of we traveled 360 feet. How good an estimate do you think that is? And if it's not good, is it too low or is it too high or what? What do you think about that? Someone critique my estimate. I think it's going to be an underestimate. Why is it going to be an underestimate? Okay, so for the first 2 seconds, I'm approximated by 20 feet per second. For the next 2 seconds, I approximated it by 30 feet per second. Why am I underestimating things? What do you think, Matt? What do you think? Which number am I choosing? Like this is the interval between 0 and 2. I had 2 choices, right? I had 20, I had 30. I chose 20. So what's happening? Yeah, I'm always choosing the minimum speed that I'm going, right? I'm actually, you know, I could just as well have chosen 30. So let's do that. So this is a different estimate now. Right? I do 2 times. Now for this interval, I'm going to choose the highest possible value. And so I'm deliberately overestimating now. Here to here, 2 times 38. Plus 2 times 44. Plus 2 times 48. Plus 2 times 50. Okay, so I get exactly the same thing as here, right? Because these things are all the same. The only thing is I'm replacing the 40 by 100. So I'm going 60 feet more. So this is 420 feet. That's another perfectly good estimate, but it's an overestimate, right? Okay. Now, let's say someone asks you, how far do you think they went? What answer would you give? That sounds great, right? So let's say 390 feet would be a great answer. That would be the best possible answer that we would get with the data given. right? We know that we went more than 360 feet. We know that we went less than 420 feet, right? Because for each of those intervals, I chose either the minimum or the maximum. Notice I would have gotten the same answer if instead for a different estimate, I would have used, well, let's use 25 for this, 34 for this, 41 for this, 46 for this, 49 for that. That would have been exactly the same as averaging those two. So we've seen this before, right? Remember when we did rate of change? Remember I always said try and use the midpoint as much as possible. This is the same kind of philosophy here. So in this one, it's kind of like using the left point of the function to make to do the estimate, and this is like doing the right point. And so it's always best to take the average of the two. This is integration, right? So hopefully this isn't anything too mind-blowing, right? Hopefully it's just common sense. It's just doing what we did before, but kind of doing it in the reverse direction. So instead of taking quotients to find speeds, we're doing multiplications to find distance. And because it's an accumulation, we add things together. Okay. Let's see if I can got some sleep. Whoa. Okay, that was interesting. Okay, so we kind of looked at this problem right here. I should put this up instead of doing it over there. This is exactly the problem that we looked before. Okay, now let's go from numerical to graphical. We've been doing that the whole time of this course, so this shouldn't be anything shocking to you. Okay, so this is the exact same problem, but represented graphically. And so what we do, right, to represent it graphically, we have on the horizontal axis, we have the time. So that's the input. And the vertical axis, we've got velocity. And we see, right, the points which correspond to these points over here. But in this one here, we've filled in what happens there. So let's represent now these computations we did, let's represent them graphically. Okay, so when we do a division, we're finding a slope, right? Remember, that's what we did with derivatives. When we do a multiplication, we're finding an area, right? Because if we multiply the horizontal by the vertical, that's a rectangle. And so this product here, 2 times 20, represents a rectangle of base 2, height 20, and area 40. Okay, and we can do better, right? We can assign units to it, right? Because if the base is seconds, 2 seconds by 20 feet per second times seconds equals feet. So the area here, the units of the area is feet. Seems a little strange because that's distance, but that's what it represents kind of abstractly. Okay, so this is 40 feet, this is 60 feet, etc. So each one of these things represents a rectangle. And when we add rectangles, we're just adding areas, right? The nice thing about area is it's an additive thing. If you've got one area and you add another area to it, you still get an area. You just get an area of the bigger object. Okay. So this 360 feet represents this little skyscraper kind of outline there. We can do the same thing with our overestimate, right? Instead of 20, we're now 30, 80, etc., whatever it was, 76. And now if we add up all these rectangles here, we get 420 feet. Okay, so they were two estimates. So when we do it this way, it's really blindingly obvious that this is an underestimate and this is an overestimate, because we actually see something under and something over actually graphically. So that should make it really clear. And so our estimate is 390 feet. What area is that? Well, that's like if we drew a straight line here and we kind of added in to these rectangles, we added in these triangles here, or we took these and subtracted a triangle. And so we're estimating this by straight lines. And we see that that fits pretty close, right? So it's 390 feet we would feel really comfortable with. Although we can actually see that 390 feet would be a slight underestimate, right? Because this is convex, it's concave down. And so we see that actually the little straight lines lie underneath it. So it's actually a little bit more than 390, but 390 is a pretty good estimate. Okay, so really understand this one, because this is kind of like the key concept of what makes everything work, is this kind of picture right here. Okay. So I think that's pretty straightforward. Okay. Same question that we asked before when we did derivatives. We found a way to estimate velocity from distance. Now we're estimating distance from velocity. How can we make a better estimate? And the answer is exactly the same as we came up with before. Remember, what we came up before was just do smaller intervals. Right? When we do, now the reason why that worked was when you took smaller intervals, the curve would look more and more like a straight line. And so when you do rise over run, you were getting a better and better answer because the curve is looking straighter and straighter. Here, when we use smaller intervals, it's more accurate for a different reason, right? Because when we use smaller intervals, we can see that the errors, which is the difference between the rectangles and the area under the curve, that becomes smaller and smaller. So again, by making smaller and smaller intervals, we get better and better answers. That's great. When that happens, we can do math. Like if we have a process by which we can get better and better answers, then that gives us something to develop. And that's, we can make a theory out of that. And so you see that as with the derivative, when you took a limit when you got to a straight line, here you get a limit where the rectangles, it doesn't look like you've got rectangles anymore. The rectangles are so thin, they just fill up all the curve. And so this hopefully this will convince you that, right, that the actual distance traveled is the area underneath the curve. Just like the velocity, so the distance traveled is the area underneath the velocity curve, just as velocity is the slope of the distance curve. So you're going from slope to distance, slope to area. Okay, so that's, again, another important concept that we're dealing with. Oh, hang on. Let's pause for a second. Okay, so we've done numerical, we've done graphical, so I should give you a formula problem. Okay, so let's say the velocity is 5t squared. What distance is traveled from t equals 0 to t equals 5 seconds? Okay, so remember, this is like right when we're beginning talking about derivatives. So if I asked you if this was the distance, what is the velocity at t equals 2, you would have taken a really small interval and done rise over run. Well, in this one here, what you can do is you can make yourself a little table. So we can go 0, 1, 2, 3, 4, 5. And so then we have 0, 5, 20, 45, 80, 125. And once you have a little table like this, you can do exactly the same thing as we did before, right? So we can have one estimate. We can have it as 1 times 0 plus 1 times 5 plus 1 times 20 plus 1 times 45 plus 1 times 80 is 25, 70, 150. Estimate 2, where instead of taking the left point, I can take the right point. I can do 1 times 5 plus 1 times 20 plus 1 times 45, 1 times 80 plus 1 times 125. Right, and I can get 275. And then I do the midpoint, so the average. So my answer would be 150 plus 275 is 325 divided by 2. My answer would be 162.5. Is that right? That doesn't look right. Oh,
add 62.5.
Yeah, I can't add. I forgot to carry the 1. 425. So that's 212.5. Okay, so already you can see it's more of a pain than the derivative, right? Because if the derivative, you only had to worry about one little interval. With the integration, you've got to worry about all the intervals. So that when you make your intervals smaller, that means you create more work for yourself because you create more things to do. So tomorrow I'll show you how to do this on Excel. So it's not as satisfying as differentiation. That's why we always do derivatives first, because it's kind of easy to start with. But that's my answer. And so if this was feet, this answer would be feet per second, sorry. And of course, I could have just done this straight away by taking 2.5 here and 12.5 there. I could have done that. That's a different way of doing it. And to get a better estimate, I just have to create a new table. Right? So I would do, I would add in 1/2, 1.5, 2.5, 3.5, 4.5, and then I would have figured out what the value is here. I would make myself a bigger table, do a whole lot more work, but I would get a better answer. So typically, you remember when I asked in a test question, estimate the rate of change at something, and you yourself came up with what the small interval would be. If this was a test question, I would tell you what interval to use. Just to get it to do a good interval, you actually have to do a lot of work. So it's not very satisfying. It's better to get the computer to do it, or later on we'll actually figure out formulas in which we'll be able to figure stuff out. Okay. Okay, so here is a different problem, not a distance problem, but still a rate of change problem. And you should be comfortable in thinking of a rate of change problem the same as you would think of as a distance and velocity problem, right? Because really a rate of change is, in a sense, just a certain type of velocity. Okay, so for example, here, this is a graphical problem, and it's to do with having a filter. Right? Okay, you don't want pollution to get into your lake, so you put a filter in to prevent the pollution coming from your treatment plant, the pollution entering the environment. But what happens is that over the 30-day life period of the filter gets worse and worse as you go in. And this is the rate at which it lets pollution into the lake. And so the question then, what is the total amount of pollution that has been put into the lake over the month? Okay? And we can kind of see that even though it's a different thing, we're dealing with different quantities, it's basically the same problem as this. Right? We can think of the rate of change as a velocity, and so we can think of total pollution, the accumulation of the pollution, the same that we can think of accumulation of distance. So over here we figure out distance traveled. Over here we figured out total pollution. It's still an accumulation, it's still a total. Okay. So what we want to do is estimate the total quantity of pollution, and we want to give bounds on what the pollution is. That's actually not so hard, right? Because we see that the rate of pollution is continually increasing So we can do exactly the thing. We can do left points, and that will give us an underestimate of pollution. The right points will give us an overestimate of pollution. The true answer will lie somewhere in the middle, and so we'll just take the midpoint to be the answer. Okay. And so we're just adding up rectangles. The base of the rectangles is 6, right? Because that's the period, that's how often we're testing, every 6 days. And the height of the rectangles is the value of the rate of change. Okay, so to do the underestimate, is 6. Well, it's 6 for all the rectangles, right? So we can just bring that out. And so it's going to be 7 plus 8 plus 10 plus 13 plus 18. And the overestimate is going to be 6 times 8 plus 10 plus 13 plus 18 plus 35. Okay, so that's 15, 25, 38, 48, 56. 6 times 56. This is 6 times 84, I believe, which is 336 kilograms. And this is 480, 504 kilograms. Okay, so we know that between 336 to 504 kilograms of pollution, that seems like a lot of pollution in the area. And so our best estimate is, what's this? 840 is 420 kilograms. And we would be pretty confident that's a pretty good answer. How are people feeling about this? Is this okay? Good. Right, so here is another, this is another slide sort of emphasizing the role of getting a finer and finer grid of points to do your estimates for. So if you think about it, right, usually we're interested in some interval. So there's some total interval that we're in. So here, let's, or time or whatever, right? And if we divide it into n sample points like we did over here, so here we broke it up into 5 sample points. So in here, it was, remember, it was 0 to 30, so t was 30, n was 5. That's our delta t, that's our width of our rectangle. So in this case here, our delta t was 6, and that's what we used to multiply. They were the bases of our rectangles. Okay, so there's sort of 2 things that kind of measure how fine we do, n and delta t. Delta t is the width of rectangles. N is the number of rectangles. And so the relationship is, right, the more rectangles you have, that means the narrower the rectangles are. And the narrower the rectangles are, the more rectangles you need than you use to solve the problem. So here is a problem. Okay, so we're given a rate of change. Right, that's the rate at which the bacteria are growing. Okay, so we want to figure how many bacteria there are, how many new bacteria happen over a 20-hour period. Okay. So that's our interval length is 20. Okay, so 20 is going to equal n times delta t. Just bringing this over here. Okay, so if we have a delta t of 4 hours, if we sample every 4 hours, that means we need 5 rectangles. And here we see we see 5 rectangles. And here they're using the left-hand method. So this is going to be an underestimate. Okay, so you do the 5 rectangles, you total up, and you get 252 million. Okay, what happens if we use a delta t of 2 hours? Well, if we have a delta t of 2 hours, we're going to need 10 rectangles. So here we see the 10 rectangles here, and we see that we've lessened the error. We actually can see what the error is. It's the area of all these little rectangles here. And we see that the total of our 10 rectangles now is 288 million. Is that area there. So it's more than here, but we see that we're getting closer and closer to the answer. Okay, and so next we try every 1 hour. Well, if delta t is 1 hour, we're going to need 20 rectangles to cover the 20 hours. Here's our 20 rectangles. We all add it all up, we get 307, and we see that we have a pretty small error. So we know the true answer is going to be a little bit more than 307 million. So we see that when we're doing this, we're seeing our answer is starting to stabilize. Trouble is, you've got to do a lot more work with integration than you have to do with differentiation. So tomorrow when we have a look at an Excel file, we'll see that. Right, but the point of this exercise is showing you that when you have a big N, that means your width is very small. That's going to give you good answers. So, just to finish up, we're going to have to introduce a little bit of notation. So we've talked about left-hand sum and right-hand sum. So the idea is you have rectangles and you have the base of your rectangle, that's your delta t or delta x, whatever our variable is. The height of the rectangle is going to be whatever the function is. So you can use a left-hand point or you can use the right-hand point. That's kind of like standard things that you can use. And you're going to add up a whole bunch of rectangles. So the notation that we use as a shorthand is the sigma notation. So has everyone seen the sigma notation before? Okay, good. So sigma is Greek S, it's S for sum. So this is just a shorthand way of being able to write. So what you do is you write down a generic rectangle, right? So what does a typical rectangle look like? Well, it looks like something with base delta t. That's the base of your rectangle here. So for all of them, delta t is going to be the base of your rectangle. But the height is going to vary, and the height is going to be the value of a function at some point. Right? So here, it's using, this is how you do a right-hand sum, where you do the right point of each interval. So you go from T1 to Tn. And this is the left-hand sum formula. It goes from T0 to Tn minus 1. It goes from here to here. That's just a technical detail. The main thing you've got to remember is that you have a whole bunch of rectangles. Delta T is always going to be the base of the rectangle. The height of the rectangle is going to be some f of t. It's going to be the height is going to be some value of the function in that interval. Okay, you can actually use any one, really. It doesn't really matter. This is just a systematic way of doing it. Okay. So let's, I think we're almost, how much time we've got? Oh, we've got a couple of minutes. Okay, so here's another problem. Different from a velocity problem, but really the same as a velocity problem. Okay. A drug leaves the body at the rate of 20 nanograms per minute at the start of a 10-minute period. And the rate of decreases continually declines until it is 8 nanograms per minute at the end of the time period. The total decrease in the amount of the drug in the body during this time might be okay. Let's have a think about this. Let's think about units. We see two different units here, nanograms per minute and nanograms. What has to be the correct answer? Nanograms, right? Nanograms per minute is the rate of change. We do it over minutes, so we do nanograms per minutes times minutes, we're going to get nanograms. So straight away you can eliminate C and E. Okay, so in a 10-minute period, right, so what does the graph look like? Well, it starts at 20 and it goes down to 8. So it goes down somehow to 8. We don't know exactly how. It could be like this, it could be like that. Who knows what it's going to be like. Okay. But it's going to be within this rectangle and it's going to be over this rectangle. Right? So we can come up with over and under estimates. So an over estimate would be 200. An underestimate would be 80. It has to be something between 80 and 200. So what's the only possible answer? Yeah, A. So it seems like when you look at this question that you just don't have enough information, but you do. Once you think of this picture, you can see that 12 nanograms is too little, right? Because if at worst it's releasing at 8 nanograms per minute, over 10 minutes it has to release at least 80. So this is no good. If the maximum is 20 nanograms per minute, over 10 minutes, the most it can get rid of is 200 nanograms. So this is way too much. So this is the only one that's got the right quantity and the right units. So actually, it turns out to be not that hard of a question once you actually think that through. Oh, time to go. Okay, I'll talk about this tomorrow.